right, we'll make a start then. Good afternoon, everyone. My name is Christine Chung. I'm from the Australian Bureau of Meteorology. I'd like to start by thanking everyone for joining us today for our webinar, Understanding Australia's Future Climate. So I'd just like to start with acknowledgement of country by acknowledging the traditional custodians of the land on which we live in. We pay our respects to elders past, present and future and recognise the important role traditional knowledge plays in understanding Australia's future climate. So today we have a two-part webinar from two members of the NESP Understanding Climate Variability Project. So the first part will be presented by Dr. Shayne McGregor from Monash University. Shayne is a leading expert on tropical variability. He was a lead author on the latest IPCC report, which we'll talk about today. He was also a contributor to the AR6 regional fact sheet for Australia, which he presented at the recent COP26 event. So today he'll be giving us an overview of the latest IPCC Working Group 1 report with a focus on implications for the Australian region. Following that, Dr. Wenju Cai from CSIRO, who is a world-leading expert on tropical Pacific and Indian Ocean dynamics and projections, will be presenting. He is currently the co-chair of the CLIVA Scientific Steering Group and a fellow of the Australian Academy of Science. I'd just like to say that he and his team have made very significant contributions to NESP research over the past 6 years, and he will be speaking today about El Nino Southern Oscillation, the Indian Ocean Dipole, and how they're responding to a warming climate. Also say that this webinar is being recorded and will be uploaded to the NESP YouTube channel shortly. So I'll stop sharing my screen so that Shayne can share his. Thanks, Shayne.
So can you guys all hear me? Yeah, okay. Thanks very much for the introduction, Christine. So I'm Shayne McGregor and we're talking about regional climate of Australia and talking about those AR6 projections. But before I go any further, I just want to thank people who collaborated with me in making these slides and preparing the regional fact sheet. So we kind of got input from the IPCC AR6 lead authors here. So we got Rosh Ranasinghe, Pandora Hope, Blair Truen, Olaf Morgenstern, and Nicholas College.
Sorry, Shayne, just to let you know, I think you're sharing your PDF and not the slides.
Okay.
We can see lots of pretty plots.
You can see what? Pretty plots. See, okay. I've never had this before, so I'm okay. What were you seeing?
We were seeing Yosemite 5 biases in the Atlantic.
Okay, can you see my slides now?
No, you might have to stop sharing and reshare.
Okay. I've never had this issue before. So I'll just try to share just the PowerPoint slides then. How is that?
Yeah, that's great. Thanks.
Okay. All right. Okay, so I kind of acknowledge the people who helped kind of put together the regional fact sheet and these slides. So I'm going to start with just briefly introducing the shared socioeconomic pathways and the resulting global mean temperature response before we dive down into Australia's future climate. So a scenario is basically, a what if, what if this was to happen? And these scenarios are developed based on a coherent set of internally consistent assumptions about key drivers. So you might think about, population change or economic growth. All of these things will factor into our future emissions. Now, as part of the AR6 process, so we started with those shared socioeconomic pathways, and then the next step is to try and, from that, get out the greenhouse gas emissions. So this is where, RCPs are basically prescribed. So we're talking about representative concentration pathways. So from a working group 1 perspective, what matters for us is the actual emissions, so the actual greenhouse emissions and how much of them and what kind of concentrations they are in the atmosphere. The difference between AR6 and AR5 is that AR6 had this, we started with the shared socioeconomic pathways and then moved forward to the emissions, whereas AR5 basically skipped a step and they just started with the RCP, so just the concentration pathways and moved forward from that without really considering the backstories that went behind that. So of these SSPs that are defined, there was 9 of them defined for the AR6 process, but only 5 of them were moved forward and used in the modelling. So of these 5, so you can see there's the SSP 1-19, SSP 1-26, and then I'm not going to read out all the numbers, you can read them for yourself. They were defined or utilised for 2 reasons. So 3 of them were utilised, the ones that are circled in green in the lower left-hand panel, basically for continuity with previous IPCC reports, so continuity with AR5. And then there was 2 other scenarios. So there was the SSP 1-19, so it's in the magenta circle, and the SSP 3-7.0. They were utilised to fill gaps that were missing from previous scenarios. So I'll speak specifically about this, the 1.9, the SSP 119. That was a super low emission scenario, and basically that was introduced to try and get temperatures that fell in line with the Paris Agreement, where there was an actual upper limit of 2 degrees warming with a target of 1.5 degrees Celsius. All right. So as expected, when you're looking at the model outcomes from these scenarios, obviously the amount of emissions, the amount of greenhouse gases you have in the atmosphere is incredibly important. And we can see that with this plot in the right-hand side, you've kind of got these, the 5 separate pieces in the right-hand side that are moving into arrows. And the colors in these display the temperatures from lots of the different models. So as you're at the bottom of each of the arrows, hopefully you can see my cursor. This is at the lower end of the temperature change, as well as the upper end of that box is the higher end of the temperature changes. So there's the multi-model is represented within each of these little panels. You'll also see, I suppose as we're moving up the page, you can see as the emissions are getting higher, we can see these deeper and darker reds, almost to the point where almost at the kind of black color of 6 degrees when we're talking about the very high emission scenario, that 585. But you can also see these dashed vertical lines. So the dashed vertical line with the curved arrow indicates when the emissions are meant to peak. So global greenhouse gas emissions are meant to peak. And then the next one with the half sign is when you're halfway through your decay process back to 0. And then the 0 is identified. So you can see when we're looking at the very low and low emissions pathways, they're actually reaching the peak greenhouse gas emissions today, okay, and drastically kind of reducing our emissions kind of moving forward, such that there's 0 emissions, by roughly 2060 in the very low scenario, and in the low scenario, that 0 emissions around the 2080 mark. So before I kind of move on to the regional projections, I wanted to highlight, I suppose one of the key differences between this AR6 report and previous reports. And that is there's a renewed focus on global warming levels. And this basically came about by the Paris Agreement setting a limit, saying, oh, well, we want to cap warming at 2 degrees and we're going to target 1.5 degrees Celsius. So it came with the idea of, well, what does the world look like at 2 degrees? So this is actually quite different to how it has normally been presented in previous reports. So you can see on the right-hand side here, this is typically how our temperature uncertainty is displayed. So if you were to follow the red line here, or kind of that kind of background shading, that background shading is meant to give you a representation of the ensemble spread. And when we think about this plot, what we're actively doing this time around is, rather than kind of looking at the the ensemble spread, saying, well, what's going to happen in 2080, we're kind of slicing this diagram from left to right rather than looking at it vertically. And we're saying, well, it doesn't actually matter when we reach this target, just what does the climate look like if we get to 4 degrees, or what does the climate look like if we're at 2 degrees Celsius? And so what we're not interested in is how much greenhouse gases it takes to get there. That's a different question. Or how long will it take to get to that point? Again, that's a different question. So what this does, it allows us to kind of reduce this uncertainty and just focus in on, what does the climate look like and what's the regional uncertainty at this given warming level. So I suppose it allows us to group our uncertainties and separate ones that we're interested in from ones we're not. So that was a key benefit from targeting these kind of global warming levels. All right. So I'm going to move on now with Australian common regional changes. So from the historical past, we've got this plot in the centre here, looking at temperature trends since 1960. And then you can see Australian average temperature anomalies in the top left-hand plot from 1910 through to 2020. And what you can see is that Australian land areas have warmed by roughly 1.4 degrees Celsius since 1910. And you can see this, this warming has kind of been quite prominent since around the 1950 mark. And now we're very aware that the climate we're experiencing today is well above what you would consider from internal variability, in those earlier periods or in that pre-industrial period. So we know that the anthropogenic signal has emerged above the natural variability. So we're very confident that these changes are due to the human influence. It's also important to know that the average temperature of Australia, that 1.4 degree warming, is above the global mean warming. So the global mean warming is around 1.1 degrees Celsius. And the reason for this is basically just that the land typically has a lower heat capacity, so it heats up faster. So when we have a projected warming, we're seeing it's amplified over the land areas, and the ocean areas are typically holding it back or reducing that warming. All right, so now we're kind of moving on with the projections, and I suppose that land-sea contrast is really apparent in these figures. But what we've got on the left-hand column are the annual maximum temperatures at different warming levels, and in the right-hand column is the annual minimum temperatures for these warming levels. So the first dot point here is that heat extremes have increased, cold extremes have decreased, and these are projected to continue into the future. And obviously the warming level has a large impact here. So we can see this maximum temperature has very large differences. If we're looking at the 4 degree scenario, we can see our maximum temperature can go up by somewhere in some places by 6 degrees Celsius. We also know that when you're thinking about heat extremes, temperature thresholds are really important. So we know heat, so humans and agriculture are sensitive to temperature thresholds. So if we think about a 35 degree temperature threshold, we know in the projected future, if you're going in the middle of the range scenario, so this RCP 2.45, which kind of ends up somewhere around with global warming around that 2.5 to 3 degree level. Under that scenario, the number of days that you would have above that threshold, above that 35 degree threshold, varies a lot spatially, but it's about 50 to 100% more than what it is today. So there's almost a doubling of those number of extremely hot days. And if you're actually looking at a 40 degree threshold, there's almost a 200% increase. The spatial variability kind of decreases. There's a much larger increase for these higher temperature thresholds. There's also, we've observed an increase in marine heat waves and ocean activity, ocean acidity, and that's projected to continue into the future. And we've seen enhanced warming in the East Australian current region. So this is this region off the east coast of New South Wales, Victoria, and Tasmania. You can kind of see there's I suppose a brighter red, and it's much more apparent in these 4 degree warming ranges. So this has been observed, and it's projected to continue. So we've got kind of very high confidence with that as well. Moving on to look at precipitation, I suppose when we're looking at annual mean precipitation, which is presented in the left-hand column, we can see the magnitude of the changes appears to scale with the warming, which is interesting. We also know that the sign and the magnitude of these annual precipitation changes is not significant over all of Australia. There are lots of places there's disagreement within the models, but there are some places where we will find agreement. And I'll talk about those when I start talking about regional differences later. The one thing they do have in common, if we focus on the right-hand column here, which is maximum precipitation, which is just the daily maximum precipitation for any year, we can see the daily maximum precipitation almost over the entire of Australia increases, and that increase depends on the warming level. The physical reason for this is as we warm the atmosphere, its ability to hold water increases. So for each 1 degree Celsius, it can hold 7% more water vapor. So that means when we have conditions that are useful, the conditions that generate severe storms or generate rainfall, if we put more moisture in at the bottom, we're going to generate more rainfall throughout that process. All right. The next thing we're going to discuss is fire weather. So we've got the frequency of extreme fire weather days has increased over the historical period. And we also know that the fire season has become longer at many locations. Now we expect the intensity, frequency and duration of these fire weather events to increase, and the magnitude of this increase does scale with warming level. And I think this is due to several factors, but I think the most prominent factor in this increase is due to just the warming itself. So kind of without having to consider changes in moisture availability. Right, so now onto coastal impact. So we know sea level rise has risen at a rate around Australia over the last few decades that is higher than the global average. So the rate around Australia was 3.65 millimetres a year, and the global average is 3.25 millimetres per year. And this has led, just the sea level rise in itself, not the fact that it's higher than the global average, has led to the retreat of sandy shorelines at lots of locations around Australia. We know moving forward, we're expecting relative sea level rise to continue to increase through the 21st century. And I suppose there's a little bit of uncertainty in regards to the emission scenario, how much sea level rise we're expecting. But by 2050, that uncertainty between emission scenario isn't really apparent. So between now and 2050, we're expecting roughly 20 centimetres of sea level rise, global mean sea level rise. So on top of the roughly 20 millimetres of sea level rise, on top of the roughly 30 millimetres of sea level rise we've already experienced. We know, I feel like I've got that wrong, I apologise. We know that increase in sea level rise is going to lead to increase in coastal flooding and increasing shoreline retreat along sandy coastlines throughout Australia. And in the absence of additional, I suppose there's a caveat here that this shoreline retreat is in the absence of any physical barriers or sediment sources and sinks. So there are some locations, obviously, that have physical barriers, so we're not going to get a shoreline retreat regardless of how much sea level rise that we have. We know with the increases in temperature, the snow cover and snow depth have decreased, and these are projected to decrease further with increase. And obviously the amount of this decrease depends on the magnitude of the projected warming. So whether we're ending up at 1.5 degrees or 4 degrees Celsius. And I suppose we've already spoken about extreme heat, like as in just a given threshold. But if we think about climatic impact drivers, so we think about heat waves, so these are extreme temperatures that are lasting several days, or we're thinking about droughts or floods, we're expecting these to be more widespread for higher warming levels. So we're going to see larger changes in those climatic impact drivers at 2 degrees than what we would expect for 1.5 degrees. All right. So now I'm just going to focus just quickly on some sub-regional kind of differences for Australia. So Australia was divided up into basically 4 main regions: a northern, a central and a southern region, and also an eastern region. So now we're just going to talk about the things that are different between those regions. So starting with the northern region first, we've got this observed increase in annual mean and heavy rainfall. So we can see that in the image here during DJF, you can kind of see a lot of these green colours, and the locations where there are not X's indicates there's a statistically significant trend. We can also see that the rainfall increase in this time series in either the purple bar chart or the running mean in those kind of black lines. Looking in June, July, August, we can see that there's obviously not a lot of rainfall in the region, so there's no significant trends in that season. We also know for that region, the projected mean rainfall changes are uncertain, so I think it's kind of fair to say that roughly half of the models are projecting an increase and roughly half are projecting a decrease. So averaging over them, there's kind of very little robust signal, but there's lots of uncertainty in that region. So this is a real key area to understand moving forward. But as I said before, there's a projected increase in heavy rainfall for this region and throughout the entire Australia. And this is then going to be linked to an increase in river flooding, which we're expecting to see by mid-century. For the region, it's also influenced by tropical cyclones. So the frequency of tropical cyclones is going to be important. And what we're expecting in that instance is a slight decrease in the number of tropical cyclones, but then an increase in the intensity of those tropical cyclones because there's more moisture available in the atmosphere. For Central Australia, again, we've got this projected increase in heavy rainfall and river flooding. And for Central Australia, I suppose the only real kind of key difference is that we're expecting to have more warming in this region than any of the other Australian regions. And this is just basically due to its distance from coastlines and the amount of coast that it's exposed to. So you can see in these two images here in the bottom left, the largest warming is occurring in this kind of Central Australian region. And as the regions are kind of getting closer to the ocean, the warming impact is becoming a bit mediated, a bit milder in those regions. Okay, now Southern Australia, when we look at kind of Southern Australian rainfall, you can see there is some regions of significant trends over the longer period. So looking in this panel D, again, they're looking for the regions without the X's. And it's, there are some regions that are apparent in DGF with a slight increase in rainfall. But then if we're looking at June, July, August, there's a decrease in the southwest and there's a decrease in southeast Australia. So you can kind of see the time series for the southwest Australia here in the red and black, and then below that for the southeast in the brown and black. What's clear is that the rainfall changes in the southwest are definitely stronger and more prominent than what's happening in the southeast. In fact, if you kind of separate around the 1970 mark, it's the rainfall since 1970 is roughly 20% lower than the rainfall before 1970. So it's actually been quite a significant decrease in rainfall for that Western Australian region. We also know that this is a feature that's represented in climate models quite well, and we can show that it's due to the anthropogenic influence. So what we're expecting is that there's the rainfall in this region is very likely to continue decreasing under all future scenarios. In fact, I was reading earlier today that they're projecting that by the end of the century, it may actually be somewhere up to like a 50% decrease in rainfall for that region. So we know that these projected changes are occurring mostly in the cool season. So in the plot, you can just see the plot just got updated. In the left-hand column here, we've got the annual total precipitation, and the red outline boxed is this Southern Australia region. So you can see the Southern Australian region has large-scale drying, and the magnitude of that drying is increasing with the warming level. There's also that increase in kind of short-term or maximum precipitation, even in regions that are displaying and drying. So that this southwestern WA drying is meant to be more noticeable or more noticeable during the cool season, and it's going to lead to an increase in aridity and an increase in meteorological and agricultural droughts. Okay, and I think this is kind of coming up to my last slide before I'll hand over to Chai. So for Eastern Australia, there's a projected decrease in mean cool season rainfall. So what we've got plotted here is the annual total precipitation. So it's not displaying as clearly as we would have expected. And same as all the other regions, we're going to have, even though we've got this kind of drying in the cool season, there's more extreme kind of wetting events. And then we're also expecting an increase in agricultural and ecological droughts to increase at 2 degrees global warming and greater. So for these higher thresholds, we're going to see more likely agricultural and ecological droughts. All right, so that's me done, and it's time to hand over now to Chai, who's going to tell us all about projected changes in Australia's climate drivers. So I will stop sharing my screen.
Okay, you can see my screen. Can you see my screen?
Yep, all good.
Okay, that's good. Okay, thank you all. Thank you for attending and thank you for the opportunity to present this work. It is actually a lot of people's work, particularly my colleague Gojian Wang and Agus Santoso, Benjamin. And I'm going to talk about ENSO and the IOD because we know they affect us quite dramatically. So we all know about El Nino. So during El Nino, warming in the east shift atmospheric convection to the east. Atmospheric convection always follows where the maximum temperature is. And so Australia tend to have drought condition during El Nino. And of course, this is a positive feedback between the wind, reduced trade wind, rainfall, temperature gradient, and thermocline. It's a positive feedback. Now, during El Nino, those rain band, the strongest rain band in the Pacific is the Intertropical Convergence Zone, ITCZ, or the South Pacific Convergence Zone, SPCZ. They tend to converge because of this warming. They tend to converge towards the equator, causing drought and flood, depending on where you are in the South Pacific country as well. And so they are linked to extreme. One of the extreme El Nino was 82, 83, and 97, 98, or the recent one, 2015, 16. And so we tend to have a very severe drought condition in Australia, and that is linked to our bushfire as well. La Nina is the kind of opposite. So cooling in the Central Pacific, Eastern Central Pacific, push that to the convection more concentrated and more intense in the maritime continent. And we tend to have floods. And right now, because we are having a La Nina, maybe finishing, but we are having a drought a flood in Brisbane at the moment. And so it's a sort of kind of reverse of the El Nino conditions. So yeah, Brisbane and many other parts of Western Pacific country tend to have flood in the La Nina years. And scientists, as you all must be familiar, we use a sea surface temperature in the Eastern Equatorial Pacific region called Nino 3 to describe Eastern Pacific El Nino. We know there's also different kind of El Nino with warmer normally in the Central Pacific, so Central Pacific El Nino. And you can also use a combined index of sea surface temperature in the, straight across the two regions, so Nino 3.4. So because of the vast impact of the most consequential impact of ENSO, the response of ENSO to greenhouse warming is one of the most important questions in climate change science. However, for many generations, there is no intermodal consensus. So here I'm looking at a plot from CIMMYT 5, looking at the Nino 3 standard deviation, the SST standard deviation in the 20th century and 21st century, red 20th, and there is no intermodal consensus, about half and half. So basically that has been a long-term issue. However, many models do produce a strong agreement on the mean state change, and that includes the faster warming in the Eastern Equatorial Pacific. And so that means even if temperature variability does not change because convection follows where the maximum temperature is, you would be able to see more rainfall, more convection centers shift to this more occasions shift to the east. So more extreme El Nino in terms of rainfall. And the other means that change is that maritime continent is warming faster than the surrounding region. So when the condition is right for La Nina, for the convection to be concentrated in this region, it could be more intense. So you tend to have more extreme La Nina. And the thermocline is shallowing in the future and the climate change. And so this is good for cooling in this region, also conducive to La Nina. And if you average across the warming in the Equatoria as compared to the off-equatorial region, the Equatoria is warming faster, so that those convergences on those rain band, ITCZ and SPCZ are easier to ship towards the equator, even if temperature variability does not change. And so basically that is what is expected. For example, the swing of the SPCZ towards equator increases. Each one of these break dot is one year. In the future and present day climate, it almost doubles. El Nino frequency in terms of rainfall anomalies, one of these break dots increases from 1 in 20 years to 1 in 10 years, doubles. And if we follow the Paris Agreement and you can achieve those targets, the maximum warming would arrive at around 2050, but the frequency of extreme rainfall events, El Nino rainfall events, would continue to increase for another century. So the maximum risk is not where the maximum temperature, global mean temperature is. And extreme La Nina increases in frequency, as I just talked about. But there is a lot of evidence to suggest that the sea surface temperature variability may actually increase. And so this is published 3 years ago. So I'm going to talk a little bit about that because sea surface temperature variability is such a fundamental variable that underpins the impact of ENSO. So I mentioned about we use linear theory to describe how ENSO may change under global warming, but we know that it's different kind of ENSO. So one index is not sufficient. And if we use linear theory, we also have implicit assumption that every model simulates the same anomaly center as in the observation and across all models. And that is not quite true. The bottom line is to describe El Nino, you need more than one indexes or more than one patterns. And to get the diversity of ENSO, you actually need 2 patterns, and we can get through mathematical manipulation to the 2 called EOF analysis, 2 patterns, and each pattern, this is from observation, each pattern had a time series, and we can plot their relationship. So this is the time series associated with this pattern, and this associated with the second pattern, and you can imagine during El Nino, for example, extreme El Nino, like 82, 83, is the difference between those 2 patterns because the time series for EOF1 is positive, for EOF2 is negative. So it's a difference. So that gives you the maximum warming in the east. For Central Pacific El Nino, the time series for the 2 patterns are both positive. And so you can get the sum of the 2 give you the maximum warming in the Central Pacific. So you can construct these 2 indexes. In other words, you can actually get a diversity by subtraction and addition of these 2 patterns. And there's good dynamics. A lot of paper describe the dynamics. And that dynamics is due to atmospheric convections in the east that is very hard to establish because it's cold and dry. Only when it warms to a threshold value where convection can occur, then you've got this positive feedback. La Nina is the opposite of the sum of these 2 patterns, but reverse sign. So we can have Central Pacific Index and the Eastern Pacific Index constructed in this way to describe those diversity. And as I mentioned, that this is a nonlinear process because convection doesn't occur immediately when it warms. It only need to warm a little. It has to warm a little, past the threshold value. So it's a nonlinear function, and we can use PC2. Second pattern is a nonlinear function of first pattern. This is all too technical. You don't have to worry about that. But there is a measure of these nonlinearities, and we can apply this analysis to models, and we can get to see how models perform in simulating those processes. So across the 34 simplified models, we can do that analysis. We can get the Eastern Pacific pattern in all the models. And this is one model. And this is another model. You can see the pattern are very different, although they are all Eastern Pacific El Nino in each of the models. So they are not able to be represented by one index, Nino 3. They should be represented by the model's own index, Eastern Pacific Index. So that's to say, if we use this index, we are measuring the variability at that model center, unique to that model. And so that's what we are going to do. And it turns out that not many models to produce the processes. Only about half of the 34 models, 17, produced about half of the observed nonlinearity. But if you look at those 17 models, majority of models produce an increase of 20th century improved, 21st. So majority of models, 15 out of 17 models, produce an increased SST variability. So this is basically the first study to say that it is a consensus if the model can get the nonlinear dynamics right. And CIMIC 6 has a huge improvement in simulating the nonlinear dynamics. So at the time when we do this study, that was last year, we had 27 models. 23 out of 27 models produced half of the observed processes, half of the strength. And all the 23 models produced an increase in SST variability in the Eastern Pacific Center. And 17 out of the 23 produced the Central Pacific SST variability, an increase. And so the intermodal consensus become much, much stronger. And because the majority produce increase, whether in the Central or Eastern Pacific region, we can now go back to use the Nino 3. Remember, that's the combined indexes. And once we do that, we can come back to the IPCC's assessment. IPCC reaffirmed that rainfall variability drop or extreme rainfall would increase in a bunch of scenarios. But they also said that there is no model consensus for a systematic change in the intensity of surface temperature variability over the 20th century in any of the scenarios, which is quite at odds with our analysis. So if we compare the 21st and 20th century in a 100 years chunk each and calculate the standard deviation of Nino 3.4 in the high emission scenarios, a majority of models, 38 out of 43 models, 20th century in green and 21st in purple. A majority of models produce an increase. Even the Paris Agreement's emission scenario. This is a 126 that could take us to the target of Paris Agreement. There's more than 80% of models produce an increase in sea surface temperature variability. Seeing in another way, if you plot the 20th century variability against 21st century, this is the two scenarios that I just talked about. But you go to the other scenario, 245 or 370, 80%, nearly 80% produced an increase in sea surface temperature variability. So I think that sea surface temperature variability increase should be considered seriously. And now I'm going to talk a little bit about the Indian Ocean dipole. You know, Indian Ocean dipole is a strong precondition for our bushfire in southern Australia, southeastern Australia. So the pattern is a cousin of the ENSO. So cooler, anomalous cooler in the east is accompanied by a warming in the west, and that drive an easterly wind anomaly which push warm water further towards the west. It also drives upwelling, cold upwelling in the east. And so again, it is positive feedback. And the warm anomaly support the convection in the region, leading to a huge flood, landslide in East African country. By contrast, in the Sumatra, Java, or Southern Australia, we have drought. In Australia, because the moisture that support rainfall in Southern Australia come from this region. So during positive IOD events, we had drought in our main season. of main rainfall season of June, July, August, which coincide with development IOD and peaking season. And these are the main rainfall season for Southern Australia. If you don't get the rain, summer is a dry season, bushfire will be much more serious. And in the initial IOD paper, they use a dipole index, DMI, west minus east. So positive means cooling in the east. And the last extreme IOD, positive IOD event was 2019, that coinciding with our black summer. So flood in India, in Southeast Asia countries, and East African country in 2019, many people died, millions displaced, while we were having that devastating bushfire. And it has long-term consequences. So there's a paper coming up in PNAS saying that the fire from Australia in this year, 2019 and 20 is going to inhibit the recovery of ozone. Something happened outside now. Recovery of ozone, yeah. Again, the similar story, there is no intermodal consensus on the fundamental sea surface temperature variability, but model produced a stronger warming in the west than in the east. So similar story, that even if temperature variability does not change, convection is easier to ship to the west, and so that has impact on rainfall. So this was the first paper showing that we are going to have more extreme IOD in terms of rainfall anomaly. So one of these dots is an extreme IOD rainfall or drought event, 20th century, 21st century. The frequency increases from 1 in 17 years to 1 in 60 in 6 years. And in contrast to El Nino, though, if we can get the Paris Agreement target after temperature stabilize, the extreme IOD event actually stabilizes it in terms of rainfall. So coming back to the fundamental issue of how sea surface temperature may change. In addition to the extreme particular IOD event in 2019, we also have some other events, 64, 94, and 97. And these are the anomaly patterns, sea surface temperature and winds. You can see that strong cooling in the east. And this is where the convection, the rain band is situated in the west and northern Indian Ocean. There's huge suppression of convection in the Sumatra Java region. And that's what caused our drought in Australia and Sumatra Java. And there's huge involvement of the along equatorial temperature. So this is depth. Cooling is involved because of that positive feedback, additional positive feedback because of the equatorial processes. And this pattern is very different from moderate IOD events, 82, 90, 87, and 2015. So these moderate events tend to be dominated by warming in the west. Now, convection, of course, is also suppressed, but not as much. They all move to the west and north, but in the Sumatra Java is not as much suppressed. Upwelling is not as much involved. The oceanic process is not as much involved as in the extreme. So the positive feedback in the equatorial region, along the east-west equatorial region, is not as strong. And these patterns are so different. So you need indexes to describe the diversity, and you can use the same trick as we do to El Nino, which I talked about this already. So you can get two patterns, and you can do as addition or subtraction to get the extreme as different from moderate IODs. So these are the dominant patterns for after you separate. So you have a UF1, UF2, and nonlinear relationships similarly, quadratic nonlinear coefficient. So extreme or strong IODs in this quadrant, those both time series are positives. So it's the sum of these two patterns that will give you a strong IOD event. And you can define a strong IOD index as the sum of those two time series, PC1 and PC2. And the moderate IOD is actually the difference between the two. So you have this different, minus that, you get faster warming, and there's a different dynamics, which I will not go into it, but we can describe the moderate IOD index. And these two indexes, S index and M index, are independent, are sort of orthogonal, mathematically speaking. So we are able to separate the observed BMI index into two indexes. And so we can then look at how, using this way, to apply this analysis to all models in the world. And we applied to combine CIMMYT 5 and CIMMYT 6. Now, IOD simulation, only 20 models out of 54 can produce these nonlinearities, this separation of strong from moderate PIOD events. Only 20 models produce half of the nonlinearities. So these are the 20 models. These are the 34 models. So we are not going to use them. So using that 20 models, we can get an assessment. But I like to say that IOD in models, again, quite different from observation and different across models. So for CSR model, this is strong IOD, moderate IOD. Yeah, moderate IOD is more dominated by warming in the West. And another model has different patterns, but we are allowing the pattern to be different, but focusing on the anomaly of each model's own anomaly center by using those indexes. And once we do that, we get strong consensus on moderate IOD SST variability, a reduction. So 20 years, 21st century. So 21st century in majority of model, 18 out of 20 produce a reduction, and multi-model ensemble average is significant. For the strong IOD events, though, is the opposite. The variability increases in majority of models. So we are expected to see less moderate IOD events, but more extreme IOD events. The total number doesn't change much. And so basically, that's the story about strong IOD. So we would expect to see more extreme drop in southern Australia if everything else doesn't change. But of course, in a warming climate, the mean condition is drying up as well. So basically, that brings me to the end of my presentation. So despite intermodal difference in the detail of El Nino La Nina pattern, and for that matter, IOD as well, a robust increase in ENSO sea surface temperature variability under greenhouse warming is projected across majority of IPCC models. The simulation of ENSO has improved a lot, but the IOD is not so much improved. But for those models that are able to simulate the nonlinear dynamics that separate strong from moderate IODs, we are expecting to see less moderate IOD events, but in terms of sea surface temperature, but stronger IOD events. Yeah, that's what I have. Thank you very much for your attention.
Thank you so much, Chai, and thank you as well, Shane, for your really great presentations. There have been a couple of questions coming through, and I would encourage everyone, if you have questions, just type it in the little Q&A box down below. So first of all, there was a question for Shane, I guess, from Catherine McNaughton. So she asked, how many more days over 40 degrees are likely for Melbourne and Victoria? 50 to 100% more days over 35 degrees. That sounds bad, but what was the percentage increase over 40 degrees?
Yeah, thanks for the question. So the percentage of increase over 40 degrees was actually 200%. So it's kind of twice twice, I suppose twice as bad. So then it's then becoming 3 times more likely than what it currently is to have days over that. The one thing I don't have, so you're asking specifically for Melbourne and Victoria, and I'm just kind of reading it like a regional summary section, and I'm trying to sift back through to find information more for Victoria, but I haven't managed to find it yet. But yeah, so it's seeming like it was at that 200%. And it's interesting because this is almost a middle of the road scenario, which is kind of where we're heading. So it's there for a 4.5 watts per meter squared forcing at the end of the 21st century. So it's middle of the road. So the high emission scenario is much worse than this. The increases are much larger.
Thanks, Shane. And we have another question, I guess, for Chai from Jimmy Cooking. Can you elaborate on potential impacts in Central Australia, as we are influenced from both the ENSO and IOD, with extremes of heat and drought as in 2019, and the potential extremes of rain at the other end?
Right, so basically the Central Australia, right? Yep. Yeah, so Central Australia is actually a difficult region because they are not as strongly, they are in the path between the Indian and Pacific Oceans, but in terms of influence. So yeah, so apart from the mean condition that was going to dry, that's going to warm a lot faster than the coastal region. It is the pathway for the moisture to transport across. So by Central Australia, are we saying that the desert? I'm not quite sure, is that the region? Yeah, but one thing is sure, so Central Australia is warming faster, and so it's going to cause those heat waves in southeastern Australia that must, because when you have a heat wave, the heat source coming from Central Australia in the desert region, right? So it's going to make our heat wave much more intense. Yeah, apart from that, I think that the other region that Central Australia is important is that ENSO's impact on southeastern Australia comes from its influence in the Indian Ocean first, particularly in the September-October season. And so Central Australia would play a part in that process. But only Central Australia itself, if we do a correlation between ENSO or with Central Australia temperature and rainfall, or between IOD and Central Australia rainfall temperature, we are not seeing a lot of signals in Central Australia. I'm not sure if I've answered the question, but yeah.
Thanks, Chai. And there was the second part to this question, which I guess I'll address to both of you. Says, with this information, are there examples of this being built into planning and budgets to better prepare? Bit of a tricky one.
Oh, yes, that's a very, very good question, right? I think I'll answer first. I think I always have that answer that the only purpose of a projection is to be proven that projection is long, because a projection of a severe, serious consequence, we take as a collective, we take actions, and that projection will be long. That is the purpose of that projection. So I'm hoping our policymakers, through our collective sort of political system of election, would take action, and that would ultimately avoid the consequence of what is projected. But I'll leave that to Shane as well. Shane, you need to open up your unmute. Yeah.
Yeah, no, I'm muting now. Yeah, I don't really, I'm not really aware. That's kind of outside of my area of expertise about the use of this information in planning. Yeah, so I'm not going to add any further to that, Chai.
Okay, thanks. There's a last question from Claire. Thanks for very interesting talks, Chai and Shane. Are the infographics illustrating vertical ocean temperature profiles for the Pacific and Indian Ocean available in your papers or online?
Say it again, the temperature.
Vertical ocean temperature profiles for Pacific and Indian Oceans.
Oh, they are available through IPCC's data sets. And so many of us process those data because to calculate the thermocline, for example, we have to have the upper ocean temperature. But there are a lot of data available for everybody to get. Yeah. So if you are interested in the mean, I think it's be reasonably easy to get those data. But if you are interested in interannual variability, you need to have a time sequence, a time evolution. There's a 3D data set from so many models. Yeah.
Chai, I also think it potentially could be related to an image you displayed, which kind of had like sea surface temperature changes and subsurface temperature changes.
Oh, yes. Yep. Just send me an email if you need those data, the ocean temperature, the image. Yeah, it's published. We have the data. Yeah. So
I should also say, I should also say that all papers published through NESP are open access, and so if you go to either the NESP 1 or NESP 2 website, they should be eventually uploaded, so it should be publicly available.
Yeah, all papers will be publicly available, but if it is, if you couldn't find an update one, send us an email. We'll be more than happy to send you a copy. So we thank you for your interest. Yeah. We want more people to read our papers.
Thanks. So we're coming up to the hour. Just while we're waiting, if anyone has last few questions, I just wanted to share a couple of things. So our variability project has just released a synthesis report summarizing a lot of the work that Chai presented. Hopefully you can see my screen coming up. Yeah, so with the help of Tani, who's done some really nice work, we've released this morning. So it's a non-technical synthesis report covering our current understanding of climate drivers, and so the IOD, the Southern Annular Mode, recent advances and open questions. So please go to the link, have a read. And also next week, there are a couple of upcoming events around the IPCC Working Group 2 report. So on the 2nd and 4th of March, there are a couple of webinars coming up. So please register your interest, I guess, get in touch with Tani or on the website. Thank you. We might have one more. Oh.
I just wanted to point out that Ramona answered in the chat. She responded to Catherine's earlier question about the days over 40. She's put a link there to a Climate Change in Victoria kind of page. And in that page, it talks about the 35-degree threshold and says by 2050, that the number of days exceeding 35 degrees will be between 13 and 21 days on average. And it was 8.3. So it's in that range of a near doubling for the Melbourne. So it's kind of consistent with what we were saying, but specifically for Melbourne.
Yeah, and I guess just a final comment from Catherine about policy responses, that the Victorian government has just released a series of climate change adaptation plans for regions, including Greater Melbourne, and for sectors including built environment, transport, natural environment, education and health, all on the DELP website. So thanks for that.
Yeah, thank you. Thank you to Ramona as well for answering that query online and pointing us towards that document.
Yeah, and so so final question from Tahiri. Yes, I think the slides and webinar will be uploaded to the NESP YouTube channel, Tani, I think. I guess later today or whenever the file's processed. If you'd like any more information, please feel free to get in touch with any of us, and we'll be happy to answer more questions. So we're coming up to the hour, so I just want to thank Shane and Chai again. Thank you so much for your time. This was really interesting, and I think very informative. So thank you, everyone, and thank you for coming, everybody. And thank you, Tani.
Bye.
Thank you.
Thanks, everyone.
Christine. Thanks, Tan.